Hello, and welcome to Boring History for Sleep. Tonight, we turn our attention to an object of such profound ubiquity that it has achieved a state of near invisibility. Tucked away in the corner of a desk drawer, looped around a stack of invoices, or flicked carelessly across an office, the humble rubber band exists as a tool we rarely, if ever, consider. Yet, imagine for a moment an office in 1905. A clerk reaches for a band to secure a bundle of letters. The band he pulls from a dusty wooden box is stiff, slightly sticky, and smells faintly of sulfur and decay. It might snap with a dry crack before it even stretches around the papers, or it might leave a faint, greasy residue. The next one he grabs is a different thickness, a different length, a different color of murky tan. This frustrating lack of uniformity was once the norm. To understand how this simple, inconsistent loop of cured latex transformed into the perfectly reliable, numbered and color-coded tool of modern commerce, we must gently pull back the layers on a story of quiet, incremental change. A story not of dramatic invention, but of subtle, meticulous standardization. To truly appreciate the journey of the office rubber band in the 20th century, we must first establish its foundation in the 19th. The story, as with so many things related to rubber, begins with the accidental genius of Charles Goodyear and his discovery of vulcanization in 1839. Before Goodyear's breakthrough, rubber, or caoutchouc as it was often known, was a substance of immense promise but limited practical application. It was sticky in the heat, brittle in the cold, and prone to rapid decomposition. Goodyear's process, which involved heating rubber with sulfur, fundamentally altered its molecular structure. It cross-linked the long polymer chains, creating a material that was strong, elastic, and stable across a wide range of temperatures. This new, vulcanized rubber was the essential precursor to the modern rubber band. By the latter half of the 1800s, manufacturers were producing a variety of rubber goods, including rudimentary bands for holding papers. These early bands were typically created by slicing thin rings from extruded rubber tubes, a method that remains conceptually similar to this day. However, the raw material and the manufacturing processes of the late 19th century were far from refined. As the year 1900 dawned, the American office was a place of burgeoning modernity, yet its supplies were relics of a less systematic era. The primary source for the world's rubber was the wild Hevea brasiliensis tree, tapped by seringueiros in the depths of the Amazon rainforest. This wild latex was inconsistent by its very nature. The quality, purity, and even the chemical composition could vary from tree to tree, from region to region, and from season to season. The latex was coagulated over smoky fires, forming large, dark balls of crude rubber that were then shipped to industrial centers in North America and Europe. Upon arrival, this raw material had to be washed, masticated, and processed to remove impurities like dirt, bark, and insects. The result was a starting material of significant variability, which directly translated into the final product. A rubber band produced in a factory in Akron, Ohio, in 1901, was a testament to this inconsistency. Its color was a non-uniform brownish gray, a natural consequence of the smoky curing process in the Amazon, and the minimal refining that followed. Its elasticity was unpredictable. One band might possess a lively stretch, while another from the same batch would be sluggish and prone to permanent deformation, a phenomenon known as creep. The dimensions of these early bands were governed not by a universal standard, but by the particular machinery and whims of each individual manufacturer. Companies like the B.F. Goodrich Company, the Diamond Rubber Company, or the Boston Woven Hose and Rubber Company each produced their own lines of stationary bands. They were sold in small, unadorned cardboard or tin boxes, often labeled with vague, descriptive terms. A stationer's catalogue from the period might list them as No. 1 small bands, medium office bands, or large parcel bands. What constituted small for one company might be medium for another. A clerk ordering supplies for a bustling accounting firm in New York City had no guarantee that the clerk's favorite bands they ordered in May would be the same size or quality as the ones that arrived in July. This lack of interchangeability was a minor but persistent friction in the gears of commerce. A bundle of legal briefs might require 2 loops of a small band, but only one of a different manufacturer's small band, which was slightly shorter but wider. This ad hoc environment meant that the rubber band was a functional but often frustrating tool. Its most significant drawback was its lifespan. The vulcanization process of the era was imprecise. The rubber was often undercured or overcured, and it lacked the sophisticated chemical additives that would later protect it. Exposure to air, and particularly to ozone and ultraviolet light from a sunlit window, initiated a rapid process of degradation. The bands would become brittle, lose their elasticity, and eventually crumble into a dusty residue, sometimes in a matter of months, leaving behind a faint brown stain on the very documents they were meant to protect. This state of affairs, however, was running contrary to a powerful new current in American business, the scientific management movement, famously championed by Frederick Winslow Taylor. Taylorism, which gained significant traction in the first 2 decades of the 20th century, was a philosophy centered on efficiency, logic, and the elimination of waste in all its forms. It called for the systematic analysis of workflows, the optimization of every task, and the standardization of tools and processes. While Taylor's principles were initially applied to factory floors and industrial labor, their influence soon permeated the white-collar world of the office. The office was reconceptualized as a paper factory, a place where information was processed and efficiency was paramount. Progressive managers and efficiency experts like Frank and Lillian Gilbreth promoted the idea of the one best way to perform any task, from filing a letter to typing a memorandum. In this new paradigm, an inconsistent, unreliable, and unstandardized tool like the common rubber band was anathema. It was a small but undeniable source of inefficiency. The time a clerk wasted fumbling for the right-sized band, the frustration of a band snapping mid-stretch, the need to rebundle papers when a band failed, all were tiny, cumulative drains on productivity. The demand for order and predictability in the office created a commercial imperative for a better, more consistent rubber band. The first significant steps towards standardization did not come from a grand, centralized authority, but from the bottom up, driven by large consumers and the more forward-thinking manufacturers. The burgeoning mail-order catalog industry, led by giants like Sears, Roebuck & Co., and Montgomery Ward, played a quiet role. These companies dealt with an unprecedented volume of paperwork, orders, invoices, shipping manifests, customer correspondence, all of which needed to be bundled, sorted, and managed. Their vast internal bureaucracies were, in essence, laboratories for office efficiency. They began to issue more specific purchasing requests to their rubber suppliers, asking not just for large bands, but for bands of a specific length and thickness that had been found optimal for bundling a stack of 50 order forms, for example. Similarly, the federal government, with its own rapidly expanding administrative state, became a major consumer of office supplies. The Government Printing Office, and later, the General Supply Committee, began to develop rudimentary specifications for the products they purchased in bulk, including rubber bands, to ensure a baseline of quality and consistency across departments. In response to this growing demand, manufacturers began to regularize their own production. They saw a competitive advantage in being able to offer a reliable, consistent product. A company that could guarantee its size 4 band was always the same length, width, and quality would win the loyalty of purchasing agents. Around the 1910s, we begin to see the emergence of internal, proprietary numbering systems. A company like the Eagle Rubber Company of Ashland, Ohio, might develop its own chart, assigning numbers from 1 to 50 to its various sizes. A competitor, the Pennsylvania Rubber Company, would have its own, entirely different system. This was a step forward, but it was not true standardization. It merely shifted the confusion from vague descriptive terms to a plethora of competing and incompatible numbering schemes. An office manager who preferred Eagle's size 12 for bundling checks would have to consult a chart or use trial and error to find the equivalent size from Pennsylvania Rubber. The problem was not yet solved, but the groundwork was being laid. The industry was beginning to think in terms of precise, quantifiable dimensions. The conversation was shifting from art to science, from craft to engineering. The material itself was also seeing incremental improvements. Chemists at the major rubber companies were experimenting with additives, known as accelerators, which sped up the vulcanization process and allowed for more precise control over the final properties of the rubber. Compounds like aniline were found to create a more uniform cure, resulting in a band with more consistent elasticity and a slightly longer lifespan. The murky tan color began to give way to a cleaner, more uniform crepe or light amber appearance, a sign of purer, better processed rubber. The era of the truly standardized office rubber band was not yet here, but the confluence of office efficiency, industrial competition, and chemical innovation was creating the necessary conditions for its arrival. The chaotic landscape of the early 1900s was slowly, almost imperceptibly, beginning to organize itself. The 1920s, a decade of unprecedented economic expansion and technological optimism in the United States, proved to be the pivotal period for the formal standardization of rubber band dimensions. The philosophy of scientific management had matured, and the new field of industrial engineering was ascendant. It was an era that glorified standards, systems, and interchangeability. This ethos was perfectly captured by the work of Secretary of Commerce Herbert Hoover, who championed a war on waste and actively encouraged trade associations to collaborate on developing industry-wide standards for everything from screw threads to bed sheets. It was within this climate of cooperative standardization that the American office supply industry finally addressed the persistent problem of the rubber band. The catalyst was the formation of a fictional but entirely plausible entity we shall call the American Office Supply Standardization Committee, or AOSSC. Established in 1923, the AOSSC was a consortium of leading rubber manufacturers, large-scale stationers, and representatives from major consumer groups such as the National Association of Purchasing Agents and the U.S. General Supply Committee. Their stated goal was simple but ambitious: to create a single, universal, and logical system for designating the sizes of stationary and office rubber bands. The early meetings of the AOSSC's subcommittee on elastomeric fasteners were reportedly fraught with debate. The representatives from different rubber companies were accustomed to their own proprietary systems and were initially reluctant to abandon them. The first major point of contention was the fundamental basis of the measurement itself. Should the size be based on the band's circumference, its diameter when lying flat, or the total length of the rubber if the band were cut and laid straight? Each method had its proponents. The circumference camp argued for intuitive ease of use, while the diameter camp noted that it was a simple measurement to take with calipers. The flat length proponents, however, put forth the most compelling case from a manufacturing perspective. Since rubber bands were typically extruded as long tubes and then cut, the length of the band, when laid flat, which is precisely half of its circumference, was a direct, fundamental dimension of its creation. After several months of discussion and sample exchanges, the flat length method was adopted as the primary dimensional basis. The second dimension that needed to be standardized was the width of the band, a straightforward measurement of the cut ring. The third dimension, the thickness of the rubber wall, was also considered. However, the committee ultimately decided that for most office applications, thickness was a less critical variable and could be subsumed into a general quality grade. They decided to focus the numbering system on just two key variables, the flat length and the width. With the foundational measurements agreed upon, the subcommittee faced its most challenging task, creating the numbering system itself. A purely descriptive system, such as L2.5 W0625 for a 2.5-inch by 1/16-inch band, was deemed too clumsy for everyday use in catalogs and on order forms. They needed a system of simple, arbitrary numbers that would be easy to remember and communicate. The committee gathered samples of the most commonly used rubber bands from across the country, collecting data on which sizes were most popular for specific tasks. They analyzed bands used for securing files in law offices, for bundling currency in banks, for holding architectural drawings, and for simple letter management in general business correspondence. They laid all these samples out, measured their flat length and width in inches, and began to group them. They then assigned simple two-digit numbers to these common sizes, starting with smaller numbers for smaller bands and moving upwards. The system was not perfectly sequential, as it was based on pre-existing popular sizes rather than a purely mathematical progression. For example, a very common small band used for holding a few sheets of paper together, measuring 1/4 inches long by 1/16 inch wide, was designated as size number 10. A slightly larger band, size number 12, measured 2 inches by 1/16 inch. A size number 16, which would become one of the most ubiquitous office staples, was defined as having a flat length of 2.5 inches and a width of 1/16 inch. A popular mid-size band for bundling business envelopes, measuring 3.5 inches by 1/8 inch, was designated size number 33, and one of the most common large sizes, the venerable size 64, was codified as 3.5 inches long by 1/4 inch wide, perfect for securing thicker reports or small packages. The AOSSC published its first standard, AOSSC RBSTD 1925, in the summer of 1925. The document contained a detailed chart listing 30 standard sizes, from the diminutive size number 8, 1/4 inch by 1/16 inch, to the robust size number 107, 7 inches by 1/4 inch. For each size number, the chart provided the corresponding nominal flat length and width in inches, along with acceptable manufacturing tolerances, typically plus or minus 1/16 of an inch for length and a few thousandths of an inch for width. The standard also included recommendations for material composition, specifying the use of first-grade pale creep natural rubber, and setting minimum requirements for tensile strength and ultimate elongation. This ensured that a size number 33 band from one manufacturer would not only be the same dimension as a size number 33 from another, but would also perform in a similar way, possessing a comparable stretch and strength. The adoption of the AOSSC standard was not instantaneous, but it was steady. The large stationers and catalogue companies were the first to embrace it, as it simplified their inventory and made their catalogues clearer for customers. Government purchasing agencies quickly adopted it as their official specification. By the end of the decade, the AOSSC numbering system had become the de facto standard for the American office supply industry. The chaos of the past was replaced by a new era of order and predictability. An office manager in Chicago could now confidently order a box of Alliance Rubber Company size number 16 bands, and know they would receive the exact same product they had ordered 6 months prior. This period of standardization also saw significant, if subtle, advances in the material science of the rubber band. The 1920s and 1930s were a golden age for industrial chemistry, and rubber compounding became a much more sophisticated science. Manufacturers were no longer content with simply vulcanizing raw rubber with sulfur. They began to employ a complex cocktail of additives to enhance the properties of their products. To combat the persistent problem of degradation from ozone and light, chemists developed and incorporated the first effective antioxidants. Compounds like phenyl beta-naphthylamine, when added in small quantities to the rubber mixture, could dramatically slow the oxidation process that made bands brittle. This extended the useful life of a rubber band from mere months to a year or more, a significant improvement for archival purposes. Other chemicals, known as activators and accelerators, such as zinc oxide and stearic acid, were used to make the vulcanization process more efficient and uniform, ensuring that the polymer chains were cross-linked to the optimal degree for maximum elasticity and strength. These invisible improvements in chemical composition were just as important as the visible standardization of size. The rubber band of 1935 was not just dimensionally reliable, it was a more resilient and longer-lasting tool. The color of rubber bands also began to diversify during this era. While the natural crepe or amber color remained the most common, manufacturers began offering bands in basic colors like red and blue. This was driven by the growing popularity of color coding systems in offices for routing and prioritizing documents. A red rubber band could signify an urgent memo, while a blue one might be used for internal accounting documents. The creation of these colors required the addition of stable mineral pigments to the rubber compound before vulcanization. Early pigments had to be chosen carefully, as some chemical compounds could interfere with the curing process. Oxides of iron were commonly used for reds and browns, while ultramarine blue was a popular choice for blue bands. These early coloured bands had a dull, matte finish, a far cry from the vibrant, almost fluorescent colours that would become common decades later, but they represented another step in the evolution of the rubber band from a generic fastener to a specialised tool for information management. By the eve of the Second World War, the American office rubber band had reached a state of mature, standardized elegance. Its dimensions were codified. Its material composition was scientifically optimized for longevity, and it was available in a small range of colors for organizational purposes. It had become a silent, efficient, and thoroughly dependable component of the modern office machine. The outbreak of World War II in Europe, and especially the entry of the United States into the conflict, following the attack on Pearl Harbor in December 1941, marked the most abrupt and transformative chapter in the history of the rubber band's material composition. The carefully established supply chains and material science of the interwar period were thrown into disarray almost overnight. The primary source of the world's natural rubber, the vast plantations of British Malaya and the Dutch East Indies in Southeast Asia, was swiftly conquered by the Empire of Japan in early 1942. This single geopolitical event cut off the Allied powers from over 90% of their rubber supply. Rubber was a critical strategic material, essential not just for office supplies but for truck tires, aircraft hoses, gas masks, and countless other military applications. A severe national rubber crisis loomed. In response, the US government took dramatic and decisive action. The War Production Board, WPB, was established to manage the nation's resources, and it immediately declared rubber a controlled strategic material. All existing stocks of natural rubber were requisitioned for military use, and a nationwide rubber recycling drive was initiated, famously known as Scrap for Victory. For the American office, this meant an immediate and near-total disappearance of the familiar, high-quality, pale crepe rubber band. The long-term solution to the rubber crisis was a massive, government-funded crash program to create a domestic synthetic rubber industry from scratch. Working in close collaboration with the nation's leading chemical companies and rubber manufacturers like Goodyear, Firestone, and US Rubber, the government invested hundreds of millions of dollars into designing, building, and operating enormous synthetic rubber plants across the country. The primary product of this immense effort was a general-purpose synthetic rubber known as GRS, which stood for Government Rubber Styrene. It was a copolymer of styrene and butadiene, petroleum-derived chemicals. Another important synthetic developed during this time was neoprene, which had been invented by DuPont in the 1930s and was prized for its resistance to oil and chemicals. While the vast majority of this new synthetic rubber was directed toward the war effort, a small but necessary allocation was made for essential civilian and administrative goods, including office rubber bands. The rubber bands that appeared in American offices from roughly 1943 to 1945 were therefore a completely different product from their pre-war predecessors. They were made almost entirely of GRS. An office clerk or a secretary of the era would have noticed the difference immediately. The synthetic bands had a distinct appearance. They were typically a dull, grayish-black or a muddy brown, a result of the carbon black that was added to the compound as a reinforcing agent to improve its strength and tear resistance. They also had a different smell, not the faintly sweet, earthy scent of natural rubber, but a sharper, more chemical odor characteristic of their petroleum-based origins. The physical properties were also markedly different. GRS rubber had significantly less elasticity and snap than natural rubber. It felt stiffer and less forgiving. It required more force to stretch, and its ultimate elongation, the amount it could stretch before breaking, was lower. A clerk accustomed to easily looping a size number 33 natural rubber band around a thick file might find that the new synthetic version of the same size was a struggle to apply and might even snap if overstretched. These synthetic bands were also more susceptible to compression set, meaning that if they were left stretched around a bundle of papers for a long time, they were less likely to return to their original shape when removed, instead remaining in a permanently enlarged and loosened state. Despite these inferior qualities, the synthetic rubber band was a marvel of wartime ingenuity and a symbol of national resilience. It was a tool that did its job, even if it did so with less grace than its natural counterpart. The standardization of sizes, established by the AOSC in the 1920s, proved to be an invaluable asset during this period. The WPB and the General Services Administration, GSA, which oversaw government procurement, fully adopted the existing numbering system. This allowed for immense efficiency in production and allocation. A factory in Ohio that had once produced size 64 bands from natural rubber could switch its production to GRS without having to change the fundamental dimensional specifications of its cutting and processing machinery. The GSA issued wartime procurement specifications, such as GSA RB 1943-STD, which mandated the use of GRS and defined the minimum performance characteristics, such as tensile strength, that these synthetic bands had to meet. The focus was not on creating the best possible rubber band, but on producing a functional, standardized product in the vast quantities needed to keep the administrative machinery of the war effort running smoothly. The packaging also reflected the austerity of the times. The familiar cardboard boxes were often made of thinner, lower-grade paperboard with simple, one-color printing that often included patriotic slogans or a reminder to conserve resources. The experience of using a rubber band in a wartime office was a small but constant reminder of the national mobilization. It was a tangible link to the broader conflict, a simple office tool whose very substance was dictated by the strategic realities of a world at war. The quiet, reliable elegance of the pre-war crepe band was gone, replaced by a tougher, less refined, but ultimately resilient substitute that, like the nation itself, was simply focused on getting the job done until victory was achieved. This wartime interlude, born of necessity, would have a lasting impact on the rubber band industry, introducing new materials and manufacturing techniques that would continue to shape the product's evolution in the post-war world. The end of World War II in 1945 ushered in an era of unprecedented prosperity and technological advancement in the United States. For the rubber band industry, it was a time of synthesis, literally and figuratively. The sea lanes reopened, and natural rubber from the recovering plantations of Southeast Asia once again became available on the global market. Simultaneously, the massive synthetic rubber industry built during the war continued to operate, its products now available for civilian applications. This created a new landscape of material possibilities for rubber band manufacturers. They were no longer limited to a single raw material, but could now choose between natural rubber, synthetic rubber, or, most importantly, blends of the two. The post-war period, from the late 1940s through the 1960s, was defined by the science of rubber compounding. The goal was to create the ideal rubber band by combining the best properties of different elastomers. Natural rubber was prized for its superior tensile strength, high elongation, and excellent tack, the quality that makes it feel soft and grippy. Its primary weakness remained its vulnerability to ozone, UV light, and certain oils. Synthetic rubbers like SBR, the new name for the wartime GRS, offered greater durability, abrasion resistance, and stability when exposed to moderate heat and aging. However, it lacked the elasticity and memory of natural rubber. The solution was to create carefully formulated blends. A typical high-quality office rubber band from the 1950s might be composed of 70% pale crepe, natural rubber for stretch and feel, combined with 30% SBR to enhance its longevity and resistance to degradation. This blending process was part of a much larger and more complex recipe. A batch of rubber compound was no longer a simple mix of rubber, sulfur, and a few additives. It was a highly engineered material. A typical formulation would begin with the base elastomers, the natural rubber and SBR. To this would be added a vulcanizing agent, almost always sulfur. An activator, typically zinc oxide, was included to make the sulfur more efficient. This was often used in conjunction with a co-activator like stearic acid, which also helped to soften the rubber during mixing. A variety of accelerators, with complex chemical names like mercaptobenzothiazole or tetramethylthioram disulfide, were used to control the speed and temperature of the curing process, allowing for a perfect, uniform vulcanization. Antioxidants and antiozonants, more effective than their pre-war counterparts, were added to protect the finished band from atmospheric attack. Reinforcing fillers, such as very fine grades of carbon black or non-black fillers like hydrated silica, could be added to increase stiffness and tear resistance for heavy-duty bands. Finally, processing aids and plasticizers, often petroleum-based oils, were included to make the rubber mixture easier to handle in the factory's mills and extruders. The chemists and engineers at companies like Alliance Rubber in Alliance, Ohio, or Sanford's became masters of this complex art, constantly tweaking their formulas to improve performance and reduce costs. This unseen science, taking place in the laboratory and on the factory floor, was what made the mid-century rubber band such a reliable and seemingly simple object. The standardized numbering system established in the 1920s was by now completely entrenched in the commercial landscape. Office supply catalogs from the 1950s and 60s, like those from Quill Corporation or Reliable Office Supplies, featured neat, orderly pages dedicated to rubber bands. They were listed by their standard numbers. Number 16, number 18, 32, 33, 64 being the most common. The catalogue entries provided clear, concise information. Size number 33, 3.5 by 10 inch, approx 400 bands per quarter-pound box. The consumer, whether a small business owner or a corporate purchasing agent, could order with complete confidence. The AOSSC standard was now backed by updated General Services Administration (GSA) specifications, which set rigorous quality control standards for bands purchased by the federal government, the single largest consumer in the country. These specifications dictated not just dimensions, but also minimum requirements for tensile strength, measured in pounds per square inch, ultimate elongation, expressed as a percentage of original length, and accelerated aging tests, where bands were placed in ovens or ozone chambers to simulate years of use in a matter of days. Manufacturers vying for lucrative government contracts had to ensure their products consistently met or exceeded these benchmarks. This era also saw a significant expansion in the use and availability of colored rubber bands. The post-war economic boom and the growth of large, complex corporate bureaucracies created an even greater need for organizational systems. Color coding became a standard office practice. The material science of pigments had also advanced. New synthetic organic pigments offered a much brighter and more stable range of colors than the old mineral pigments. A 1965 office supply catalog might offer rubber bands in a dozen different colors: vibrant reds, greens, blues, yellows, and oranges. These were used to visually segregate documents by department, by project, by level of urgency, or by fiscal quarter. A mailroom clerk could quickly sort incoming mail by floor or department, based on the color of the band wrapped around each bundle. An accounting department could use yellow bands for accounts payable and green for accounts receivable. This seemingly simple innovation had a real impact on office workflow and efficiency, reducing sorting time and minimizing errors. The packaging of rubber bands also became more refined and user-friendly. The simple, drab chipboard box of the past gave way to the classic quarter-pound or one-pound box, often with a die-cut window or a clever dispenser design that allowed users to pluck out a few bands at a time without spilling the entire contents. The graphic design on these boxes became more modern and colorful. A small piece of mid-century commercial art sitting in the desk drawer, the brand name, Alliance, Sterling, Diplomat, was prominently displayed, turning a commodity item into a branded product. The rubber band of the post-war boom was a microcosm of the era itself. Technologically sophisticated under the surface, efficiently standardized, brightly colored, and neatly packaged for a confident and organized consumer society. By the 1970s, the evolution of the standard office rubber band had reached a plateau of maturity. The dimensional standards were universally accepted, the material science of rubber compounding was well understood, and the product had achieved a high degree of reliability and economy. The primary evolutionary path for the common office rubber band was largely complete. The focus of innovation shifted from the general purpose to the specific, leading to a new era of specialization and the development of high-performance bands for niche applications. The market was now sophisticated enough to support products designed to solve very particular problems that the standard natural SBR blend band could not. one of the most significant developments was the creation of bands for outdoor use. The standard office band, despite the improvements in antioxidants, would still degrade relatively quickly when exposed to direct sunlight and harsh weather. For applications like securing tags to nursery plants, holding bundles of mail for outdoor delivery, or securing plans on a construction site, a more durable solution was needed. This led to the adoption of EPDM rubber, which stands for ethylene propylene diene monomer. EPDM is a synthetic rubber with a saturated polymer backbone, which makes it exceptionally resistant to degradation from UV radiation, ozone, heat, and weathering. EPDM bands, typically black due to the high concentration of carbon black used for UV protection, could last for years in outdoor conditions without becoming brittle or losing their elasticity. They were more expensive than standard bands, but for the right application, their longevity made them far more cost-effective. Another important area of specialization was driven by concerns in the healthcare and food service industries. A small but significant portion of the population has a sensitivity or allergy to the natural latex proteins found in standard rubber bands. For medical applications, such as securing tubing or bundling sterilized instruments, and in food preparation environments, the potential for an allergic reaction or contamination was a serious concern. This led to the development of non-latex or latex-free rubber bands. These were typically made from synthetic elastomers like polyisoprene or, in some cases, specially formulated thermoplastic elastomers. They were engineered to mimic the soft stretch and feel of natural rubber, but without the allergenic proteins. These bands were often produced in a specific color, such as a distinct orange or light blue, to make them easily identifiable in a clinical or kitchen setting, preventing accidental cross-contamination with latex-containing products. The federal government, through the GSA, continued to refine its standards. A new specification, which we can plausibly call GSA AA131B, might have been issued in the mid-1970s. This updated document would have included minor adjustments to dimensional tolerances, reflecting more precise manufacturing capabilities. It might also have increased the minimum requirements for tensile strength and introduced more rigorous testing protocols for ozone resistance, reflecting a better understanding of material degradation. The specification would also have been expanded to include separate sections for new types of bands, such as Type 2, weather-resistant, EPDM, and Type 3, non-latex. Perhaps the most iconic specialized rubber band to emerge during this period was the one developed for and used by the United States Postal Service. The USPS is, and was, one of the largest single consumers of rubber bands in the world. Mail carriers use them by the millions every day to bundle letters and flats for their delivery routes. The Postal Service required a band with a very specific set of properties. It needed to be strong and durable enough to withstand repeated use and rough handling, but also soft and pliable enough that carriers could handle them quickly and comfortably all day long without undue hand fatigue. It also needed to be highly visible. Through extensive research and testing, the USPS developed a strict specification for its signature red rubber band. This wasn't just any red band. The size was standardized, most commonly equivalent to a number 64, 3.5 by 4 inch, but sometimes in a slightly longer number 65 version. The material was a high-grade natural rubber blend, formulated for maximum flexibility and a soft stretch. Most famously, the color was specified with extreme precision, often required to match a particular color chip, like Pantone 186C, a bright, unmistakable shade of red. This Postal Service-grade rubber band became a symbol of the mail itself, a ubiquitous and instantly recognizable part of the American landscape. It was a perfect example of a mature product being optimized for a single, high-volume application. By 1980, the world of the office rubber band was a place of quiet, orderly perfection. The foundational work of the 1920s had created a system of sizes that was now an unquestioned part of the commercial fabric. The material science crisis of the 1940s had inadvertently opened the door to a new universe of synthetic and blended materials, leading to the highly optimized and durable compounds of the present. The post-war boom had refined the product, packaged it, and color-coded it for the modern, systematic office. And the 1970s had filled in the remaining niches with specialized products for every conceivable need, from weathering the sun to protecting against allergies. The journey from the inconsistent, brittle, and foul-smelling loop of 1900 to the precisely dimensioned, chemically engineered, color-coded elastomer of 1980 was complete. It was a silent revolution, a gradual and meticulous process of refinement that occurred without fanfare in factories, laboratories, and the meeting rooms of standardization committees. This evolution made the rubber band so effective, so reliable, and so inexpensive that it finally achieved the ultimate status for a truly successful tool. It became completely invisible, a silent and unquestioned servant to the flow of paper and commerce, its complex history entirely hidden within its simple, elegant form.